So this is where we kind of ended last time. What must occur? We have to have particles collide with the right orientation and enough energy. That all has to happen for bonds to break in order to have the reaction get started. And then, of course, the bonds of the products must form. So we have two processes happening at once. Energy is required to absorb and break the bonds. We say axing is taxing. And energy release when the bonds are formed. Forming is warming. That means exothermic. Now, in a chemical reaction, most of them at least, you're going to have both processes occurring. You have bonds breaking and bonds forming, and then it's the net out of those two, whichever is higher amount, as to how the overall reaction is going to look, if it's endo or exothermic. I mean, there's an occasional reaction like decomposition where basically you're just breaking bonds. So, but for the most part, everything else is going to have breaking bonds, forming bonds, and then you end up with the net of the two processes is going to determine the overall, whether your delta H is positive or your delta H is negative, whether it's endo or exo. Now, because we're talking about the bond breaking and bond forming here, this is going to be the third way that you can calculate delta H. So far, we looked at Hess's law. That's one way to calculate delta H. The next thing we looked at were the heats of formation. Remember the heats of formation? The tables, those are in the textbook, in the appendix. You can look them up if you need them for the problem set. Sometimes they're in there, sometimes they're not. But remember, the formations is the one where it's products minus reactants. That one's on your formula sheet. No problem there. However, this one is the bond breaking, bonds forming way of calculating delta H. So the equation generally looks like this. Delta H reaction is the sum of the bonds broken minus the sum of the bonds formed. And I'm going to tell you right now, this one is not on the formula sheet, and you do have to memorize it. And they do like to ask lots of questions on the AP exam about it, because it's very important that you know that bonds breaking, bonds forming, as you can see, whichever net's higher, the energy of the bonds broken, if that's higher, you get a positive delta H. The energy of the bonds forming and being released, that's going to be higher, then you're going to end up with a negative delta H. So that's a general one. So bond energies of reactants, the bond energies of the products, or if you want to abbreviate bond energy, also they can call it bond enthalpy. Enthalpy energy means the same thing, but if they say bond energy or bond enthalpy, they're talking about the energy within the bond. And you will be given a table with all the bond energies on it to pull from in order to do that. This equation, like I said though, very important. This one you have to memorize. This one's not on the formula sheet. So, and like I said, they always like to ask about it too. Definitely in some way, shape, or form. Whether it's an MCQ or FRQ, it always manages to appear on the AP exam. So bonds broken minus bonds formed, sum of that, okay? Now, for our purposes too, and for our example problems, like right here, given you this example here of this reaction, and you see the table of the bond energies, it could also be labeled bond enthalpy, okay? Now, for our purposes and for this particular section, I will help you draw them out since we haven't officially gone over drawing Lewis dot structures just yet. And for your exam test coming up, you will be given the drawn structures as well, okay? Because you're not expected to know how to draw them just yet. However, on the AP exam, they could have you draw them and then utilize those to figure out the delta H from that. So for that purpose here, we're going to start off and we're going to go ahead and draw these out, and then it becomes like a big bond counting process. Now, luckily over here, these particular chemicals up here, they're all pretty much single bonded, which is nice. Methane, if you can remember, it's nice and tetrahedral. You're going to have 4 single bonds of the C to H. And here, out of our diatomics, anybody remember which one chlorine is? Is it single bonded, double bonded, triple bonded? Single. Remember, all the halogens are single, and so is hydrogen. The only one that's double is going to be oxygen, and the one that's triple is nitrogen. So the thing is, though, there's a 2 in front of here. So that means that we have 2 of them reacting. Okay? So you have to multiply it by the mole ratio in front. Then, of course, fluorine, we just said halogens are all single bonded. And notice I am just drawing the structural here. I'm not putting all the dots around it or anything because that's kind of unnecessary. I just need to know the type of bond. So these ones are all going to be the ones on the reactant sides. These are the ones that are going to have to break. Over here on the product side, okay, now we have to look at that. CF2Cl2, okay, that means this is going to be a tetrahedral one. Those are all going to be bonded to the central atom there. So we're going to have 2 C to F bonds and 2 C to Cl bonds in that particular one. And then H to F, there's a 2 in front, so we're going to have 2 of these that are going to react. And then HCl, once again, 2 in front of there means 2 of those are going to react. And those are all single bond. And they give you this nice little table over here, as you can see, that is going to list them out for you. Now, according to our chemical equation here, we need the sum of the bonds broken minus the sum of the bonds formed. So now it just becomes a big counting game. All right. We have over here broken. We count. We have 1, 2, 3, 4 of our C to H bonds, right? So 4 times C to H, that's going to be 413, plus, okay, counting here, 1, 2, that means we have 2 times our C to Cl, 239, plus 2F to F, and that's right here, so 154. Okay, that's going to comprise all of the bonds that have to break. Now we have to also count all of the bonds that are going to form over here. And I'm just going to kind of start it below because I'm going to run out of room here, but I'm going to keep it in a bracket. So we have 2 C to F's over here. So 2 times C to F, 485. And then I have 2 C to Cl's. So like I said, it just becomes a big counting game. This is what, 339 here? Plus 2 HFs. HF, here we go, 565. And last but not least, 2 HCl's. And the HCl's 427. And then you can do the calculation. I suggest doing like all the bonds broken together and then all the bonds formed together. Definitely watching, you know, making sure you're getting the right numbers for the signs and all of that. Did anybody calculate the bonds broken side just yet? For the bonds broken, I'm getting 2438. Okay. Minus the bonds formed. Anybody get bonds formed? 3,600 and what? 32. Looks about right. So when you calculate and subtract 2438, 3,632, you should get negative 1194 kilojoules. Like so. And this, of course, tells you this is exothermic, because we ended up with a negative delta H. Gives you that little piece of information about the overall reaction.
Wait, so Miss Zach?
Yes.
Okay, so the 3 different types, like, so Hess's law, you just, like, do, like, system equations and then you add all the,
well, you can flip them, you can multiply them, but you have to make it so they can cancel down, yes, for Hess's law. And then you add up the delta H's.
The standard,
the heats of formation.
Then that's where you do the products minus the reactants, right? Like
correct. And it should say to delineate, if you see a data table and they have it listed as delta HF, right, like that, you would see the F there, and that's telling you that those are heats of formation. So you would do the products minus reactants equation.
Okay. And then when it's bond energies, then you do the reactants minus products.
Correct. And then this one says bond energies. It could also say bond enthalpies. This is when you do bonds broken minus bonds formed, which is technically reactants minus products.
Okay.
Because the ones that are breaking are going to be in the reactants, the ones that are forming are going to be in the products. All right? So really look at, yes, which set of data did they give you? If they give you a series of equations, well, you know you got a Hess's law. If you see heats of formation, products minus reactants. If you see bond enthalpies, reactants minus products, okay? So just try to keep those 3 straight, because they are, you know, can easily be misconstrued. And that is the biggest mistake that I will see in these type of problems is they'll end up doing the products minus reactants instead of the reactants minus products. So then obviously your sign's going to be wrong. Okay? So just being sure that when you see bond energy, you do broken minus form, reactants minus products.
Do we have to write in this equation and Hess's law in FRQs before we
In Hess's law, you don't need to write out an equation because you're just manipulating the series that they give you. But for heats of formation, yes, and for when you're given bond enthalpies or energies like this, you do need to write it out, but it doesn't have to be too long. Seriously, sum of bonds broken minus bonds formed, don't make it more complicated than that. And on the heats of formation one, when you're writing that out, I would really stick to delta H, F products minus delta H, F reactants equals the delta H reaction. You don't have to write out the whole complicated sum of with the N and all of that in there if you don't want to. Okay? Because I will know what you mean and they will know what you mean, because it definitely becomes cumbersome if you're writing out the entire thing that they have on the formula sheet. All right. So that's good review and also comparison. And it looks like we got it right. Okay. Different example here though. This also gives me an opportunity to go back over organic stick figures with you real quick too. And as you can see, this is a much more manageable equation here because we only have 2 reactants in 1 product. The other example was quite cumbersome because we had 3 reactants and 3 products. Now, it says calculate the energy involved and determine if the reaction is endo or exothermic. I'm also going to show you some shortcuts here that you can do with these problems to make it go faster. But before we do that, we do have to recall, like, what do these stick figures mean? I'm going to draw it up here a little bit bigger. When we have stick figures like that, they're representing organic molecules. Now, at each corner is going to have a carbon. That is assumed that you understand that each corner of the stick figure is a carbon. Now, the other thing, though, that you have to consider here is, like, this is a 1 carbon bonded to another carbon. That's 1 of the 4 bonds needed to satisfy the octet for carbon. So they're also assuming that you're going to attach the correct amount of H's to finish off the octet. Because if it's a stick figure written like this, these are hydrocarbons. All right. So if this carbon is single bonded to that carbon, that means we need how many H's? 3. So this is going to have 3 H's off of it, like so. Now this one is bonded to the single bonded to this carbon. This one over here is double bonded. So how many H's do we need for that one? Just 1, because we have 1, 2, 3, and that's the 4th bond satisfying the octet. So that means this one's only going to need 1, and this one's going to need 3 as well, like so. All right, so if you were to see that representation, you know, on the points are the carbon, and then you would add the necessary H's to finish off the octet. Now the other reactant here is Br2, which we know is just Br to Br. This right here that's listed over the arrow, does anybody know what that is when it's listed above the arrow like that? It is a catalyst. That is correct. That means it's not participating in the reaction, it is just helping to speed it up a little bit. So you won't see it in the reactants or the products. But when it's listed above the arrow like that, that means it's a catalyst, okay? Now over here with our product, all right, we have a zigzag, like so. Oh, that wasn't very good. Here, let me try again. And we have a bromine going up, a bromine going down. So what does that mean for the rest of these points? This is a carbon, this is a carbon, this is a carbon, this is a carbon. So what would we put over here to satisfy the octet of the left carbon? We need 3. Yes, 3 H's to satisfy that. This one's going to need 1 because it has 3 bonds around it. This one's going to need 1, and this one's going to need 3. Once we have all that information, now we can actually start counting bonds. But this is where you can cancel before you put it into your calculation to speed things up. Because if I have this C to H bond over here in the reactant, guess what? That cancels with this C to H bond over here in the product. So I don't have to count them into my calculation. And I can continue to do that. This one goes, this one goes, this one goes, this one goes, and so forth, right? And I go and I cancel these out so I don't have to put them in my calculation. Because if it's in the reactants and in the products, it's going to cancel itself out. Like so. So I got rid of all those C to H's. I don't have to incorporate them. Now, also there's a couple other things we can cancel. Does anybody notice which ones we can cancel? The carbon to carbon bonds. We have 2 single bond carbon to carbon bonds over here, and we have 2 single bond carbon to carbon bonds over there. So we can even narrow it down further. So then what do we need to incorporate as the bonds broken? We need to incorporate the double bonded C, so C double bonded to C, plus the Br to Br. Those are now officially our bonds that are being broken that aren't canceled. Over here, for the formed, what do we need to incorporate? We have a C to Br and a C to Br, so that's 2 of them, 2 C to Brs. And then we have 1 C to C single bond, finishing that out. That really narrows down the calculation so we don't have to deal with such numbers, huge numbers. Okay, because if you really put it in, you would have 8 C to H bonds in the reactants and you'd have 8 C to H bonds in the products. So they are just going to cancel each other out. Then all we have to do is put in our numbers now. So we have a C to C double bond here, 614, plus the Br to Br, 193. This is going to be in the reactants minus our 2 times C to Br, which is right here, which is 276, and our 1 carbon to carbon single, 348. That's much more manageable for our calculation than putting all the other stuff in. Although technically you can do that if you don't see it right off the bat. it just is gonna take you longer to do the calculation. And we all know time is precious. And if we can minimize time as much as possible and be more efficient, then we can answer more problems correctly.
Miss Zach,
Yes.
is it illegal to like have one C to C and then cross off like one of the bonds from the C double bond in C?
No, that would be yes. That you can't do that because the double bond energy isn't just double of the single.
Okay.
So no, technically you couldn't do that.
That's sad.
That's a good question though, because if you look here, the C double bonded one is 614, whereas this one's 348. They are not exactly double. Okay, so you wouldn't be able to do that. That's a good point to make here. So what do we get out of this deal here? Negative 93 looks right to me. So delta H reaction, negative 93 kilojoules. So is this going to be endo or exo? This is exo, good. Exothermic. That is correct. See, and I went ahead and did like all the calculations. I was like, oh, look what I can cancel. And then technically, I could have, you know, canceled this one and made this a 1 here. So I was like wasting my time counting all those C to H's because they ended up subtracting out. These were the C to H bonds right here.
I think we got a different answer than one of the board.
Oh, yes, I'm sorry. I did try to correct that. It is negative 93. You are right. I guess I did not edit it in here. But yes. Oh, you want to know why my answer is wrong? This is why 839. I ended up pulling out the triple bond one instead of the double one. So that's where I went wrong. So now I will fix it, don't worry. But yes, you are correct. It should be negative 93 kilojoules per mole reaction. Okay? So yes. Anyhow, my bad, but please make sure that you cancel them down. It makes it a whole lot easier. It makes you go faster. You see them, you can do that manually before you insert it into the formula. But yes, negative 93 kilojoules per mole reaction, and it is exothermic. Now your turn. Here you go. Practice. All right, so another bonds broken minus bonds formed because we see over here we were given bond energy. So sum of the bonds broken minus the sum of the bonds formed. And this is equal to delta H reaction. All right, so in this case though, they gave us the delta H reaction up here. All right, so we know that value is negative 25 kilojoules. And we're missing A to A, single bond A. So 2 of those. I just leave it as A dash A as my variable, makes it easier for me. And B to B, there's only one of them, so that's 32. Minus over here 2, and then within here there's 1, there's 2, so this is actually going to be 4 times the A to B, 46. And when you calculate, all is said and done, your AA after all the algebra is going to be what? 63.5 positive, right? Yes, okay. Now because these all go to the ones place value, everything up here is into the ones, I'm just going to also make it go to the ones, so that's why I put 64 kilojoules per mole. And that's per mole of the A to A bond, okay, the A to single bond A. Now for sketching the part B here. Now, this is where you'll get thrown off a little bit, because remember, the potential energy diagrams, that is about the formation ones, so you cannot actually like write out bond energies on it. What you need to realize though, and this is the key context clue up here, this is negative 25, so this should be what? Exothermic. So draw it with the reactant line higher and the product line lower. Then you can put in here, and sometimes they'll tell you to label the delta H as you saw before. This could be the delta H equals negative 25 kilojoules, okay? But you would want to label this is going to be PE, potential energy, and of course this is the reaction progress, like so, as you go to the right. But do you remember, like, this potential energy amounts stored in the bonds are read a little bit differently than we're talking about bond enthalpies here. So don't try to like map those out here on the graph. Yes.
For the heat of formation, is the enthalpy for those, are those the direct potential energy? Like, okay, so when we are graphing this, then we can like put in like specific values that we've calculated from the equation.
If you had the heats of formation, you could figure it out here, but we don't have that information. The only information we have is what the overall reaction is, so we can draw and sketch our graph based off of that. But do remember, like, heats of formation are all based off of the exothermic process of forming the compound, right? So forming bonds from the individual elements. Okay. So that's why, like, you can't think of bond enthalpies and heats of formation in the same categories. Because bond enthalpies really are your breaking bonds and forming bonds, whereas heats of formation were all calculated based on forming bonds from the elements at 25 degrees Celsius, 1 atmosphere. So they're different methods of finding information about what is contained and stored into the bonds.
But don't we use the enthalpy in the formation?
Yes, and I mean, not exactly. So they are calculated from forming the substance from the elements. So it technically, like, all of those would be considered formation. Forming is warming.
But this is considered like the specific enthalpy
of a specific bond within the compound.
Okay, so this one we actually do deal with enthalpies for the heat of formation of the standard. Like,
I'll have to get back to you on that.
Okay.
The origin of the numbers, although I don't think they're all that important in terms of figuring out the delta H from them, but I will get back to you on that.
Okay, but just like bottom line, so like if we have to, like, since we graphed this one, we don't know like the exact potential energy, so we just like leave it like a blank thing. Whereas if it was the enthalpy of formation, then we would be able to use like the energy that we like have from the equations.
You would, but they're not going to expect you to graph it. They just want to sketch here. Did you make the lines in the right position, because this is exothermic?
Okay, so enthalpies of like formation, that one's like the real one, and this one's just kind of like a weird inverse a little bit.
It is. They're both real, mind you. They are both real, but you're right. Though it is sort of like a weird inverse of the other way to calculate it. I agree with you there. Okay. So very good. Okay, so as you can see here, all of the steps written out if you need to go back and revisit it. And once again, don't get caught in the weeds on B. You're not trying to graph actual bond enthalpies on here. You are just showing that you realize, based off of the information provided, that this is exothermic, so your product line should be lower than your reactant line. And you can, of course, indicate the delta H being negative 25 kilojoules.